Welcome back to the corrosion failures and analysis. Today we have lecture 18, and our discussion point will be, today we will conclude the discussion on dealloying or selective bleaching, and then we will begin discussion on another corrosion form which is called intergranular corrosion. So, course is called okay. So, and the second topic we will start today is intergranular corrosion. Now, if you recall our previous lecture, lecture 17, we started talking about some of the examples what we have seen in case of silver zinc system. We have seen the example in case of nickel zinc system. In case of silver zinc system, we could get pure silver network starting from very lean silver containing a silver lean composition, silver 25, zinc 75 alloy composition. And similarly, we have seen formation of zinc oxide nanorods on top of nickel core by doing dealloying of nickel zinc alloy. Okay. That alloy was made by powder metallurgy route, which is ball milling and mechanical alloying, starting with a elemental powder nickel and zinc, and then we dealloyed in 0.5 normal Na weight solution, right, and we could get zinc oxide nanorods on top of nickel core. So, and then we started looking at dealloying in other systems. So, one system is such in steel, which is a very popular system. Here we could see that in case of 100% pearlite microstructure, we could make we could separate out cementite plates by doing forceful polarization, where dealloying of pure iron or ferrite takes place and goes into the solution, leaving behind cementite. Okay. So, here though this is not a typical of pure elements, rather one element is pure, almost a pure form, but other cementite, which is basically a compound, we can be considered as a single melting point compound. So, we can assume to be a kind of single entity or single since it is a basically stoichiometric compound, fine. So, there cementite stays back and ferrite goes out. Similarly, in case of spheroidal iron, where spheroids of cementite stays back and iron goes out in the form of iron ions into the solution. So, their dealloying takes place in the ferrite. Okay, the ferrite goes out, and both the examples I could cite for, because we have worked on that particular field in the lab. Okay. So, this is a typical example of galvanic corrosion, but that galvanic corrosion leads to a selective dissolution. Here you can say that it is selective leaching. So, let us get back to that particular example. For example, here, so this selective leaching of ferrite takes place. Or dealloying of ferrite takes place. Similarly, another example we saw in case of spheroidal steel, where initially it was pearlitic steel and then it was converted into spheroids by doing heat treatment, which is called a spheroidal heat treatment, and then we could see that preferential dissolution of iron or ferrite leaves behind the spheroids of freestanding spheroids of cementite. Okay. So, these are the examples. So, please go back and look at lecture 17 to understand these two pictures. Okay. So, now another picture, and this is the reference, if you want to see that reference, this is the reference, which is basically work we have done at IIT Kanpur. Fine. Now, this is another example where 0.43% the carbon content is 0.43% carbon. So, there we have ferrite as well as perlite. Okay. So, this is the ferrite part, this is the perlite, and this microstructure is obtained by etching in nitrile. Fine. Now, there we have two phases, one is ferrite grains, another one is perlite colony. See, perlite cannot be mentioned as a phase because it is a phase mixture. We have both the phases, one is cementite, one is ferrite. So, that is what it is called perlitic colony. Now, this ferrite grain and perlite colony, this particular microstructure we developed by nitrile etching. But now, if we start with unetched sample, polished and unetched sample, that if we do again a polarization. So, again the polarization is done and those polarizations are done in NaCl solution, 3.5% NaCl solution, and in fact, here also it is done, this polarization is done 3.58% NaCl solution. Similarly, this is also done in 3.5% NaCl solution, okay, and this is freely aerated, that means it is exposed to open atmosphere. Now, here why I am showing this picture, this actually also combines both the galvanic effect as well as de-alloying. Okay. Let us see that is what I thought that let me discuss this particular picture. Now, this is a micrograph which is developed after polarization. So, this is the kind of polarization we got at a very high value of polarization we got, okay, to the anodic part, and after that we took the microstructure. Remember, after polarization we have not done any etching. This particular picture has formed due to selective dissolution of ferrite. Okay. Now, interestingly, cementite is all the time, cementite and ferrite, this couple is considered. If this couple is considered, then this will act as anode and this will act as cathode. This happens in this particular situation happens in case of perlite colony. Okay. Now, if you take perlite and ferrite grain, so this is one grain, this is one grain of ferrite, this is another grain of ferrite, this is another grain of ferrite, okay, or we call it alpha iron, and this is the perlite colony. So, this part is basically perlite colony, and this is, you can say that this is almost a single perlite colony, because all the lamellar orientation is similar in one direction, all are in this direction. Okay. So, that is why it is a single colony. Now, in the perlite colony we have ferrite lamella and ferrite cementite lamella. So, the cementite acts as cathode and ferrite acts as anode. But when we talk about ferrite grain and perlite colony since it has a lot of cementite and cementite is cathodic in nature, overall it will act as a cathode. And this is anode. And now, anode would dissolve as per the galvanic effect in this particular solution. Now, question is, when this dissolves, the dissolution effect will be seen adjacent to where this perlite and anode, perlite and ferrite grains are in contacts. So, the dissolution pattern will be seen around this zone. In fact, we have seen this particular effect by doing AFM image, where it is very clear that if we see the depth profile, here the depth is very high and then it will become like this. So, the pearlite, this is the pearlite depth and this is in the contact point region, the depth has gone back, this is on the same level, but in the area where pearlite colony and ferrite grains are in contact, there we have good amount of the dissolution has happened quite a good distance, and then gradually the distance has gone up and then finally the ferrite grain again becomes almost of the same level as pearlite level. Because here we have in this particular region we have galvanic effect. It also relates to the point that we talked about in galvanic corrosion, that contact point is the most vulnerable region where corrosion of ferrite or corrosion of active metal happens at a rapid rate compared to the place little away from the galvanic contact point. So, this is the galvanic contact point where pearlite colony acts as cathode and ferrite grain acts as anode. So, that is what you have dissolution of ferrite close to that contact, and then as you go away from the contact point, the dissolution depth decreases gradually and finally, it becomes almost of the same level as the pearlite level. Okay. So, that means this is that is what I wanted to bring in this particular picture. Again, if you want to see this particular paper, you can see this, this is also our work. Now, this happens between pearlite colony and ferrite grain, but in the pearlite colony we have selective dissolution of those ferrite lamella, leaving behind standalone cementite. You would see that the cementite, this cementite, you see this is a kind of cementite plate, that cementite plate has bent because gradually you are taking away ferrite in the form of iron ions into the solution, leaving behind those cementite plates, standalone cementite plates. That happens because of this effect, okay, where cementite lamellae acts as cathode, ferrite lamellae acts as anode, and the anode dissolution takes place, and here anode is nothing but almost pure iron. Okay. So, this is a kind of mixed, is a combination of de-alloying in the pearlite and galvanic effect between pearlite colony and ferrite. So, this is a classic combination mode. Okay. So, now let me talk about graphitization. Okay. So, this is an example let us put, or we call it graphitic corrosion. So, these happens in cast iron. So, some book it is written as graphitization. Okay. So, this I think this is my personal opinion that this should not be used while talking about corrosion of cast iron. Okay. Graphitization means formation of graphite during cooling stage of a cast iron. Okay. So, that time if we see iron carbon phase diagram, this is a schematic picture, you can say. I am not putting all those specific values, but in schematically it is basically this is called peritectic. Okay. So, this is eutectoid, and this is eutectic points, and these are different phases are, this is liquid iron, this is delta plus liquid, this is delta region, this is delta plus gamma, this is gamma, this is alpha region, this is alpha plus gamma, this is alpha plus Fe3C, and here we have gamma plus Fe3C. Okay. And this is weight percent of carbon, fine, and this is temperature. You can go to some of the books, usual physical metallurgy book, you will get this diagram. Now, up to this point we call it, this is around 2% and this is 4.3% carbon. Okay. So, this 4.3% carbon, so between this to this we have cast iron zone, and there from here, let us say you are here. Okay. So, from there if you do a slow cooling, depending on the cooling rate, either you get cementite austenite. If you do a slow cooling, you will get graphite ferrite, and if you have a little higher cooling, you can get graphite as well as pearlite. So, those are the kind of microstructures you will get. But one such microstructure, so there are different steels called different cast irons, white cast iron, grey cast iron, then SG cast iron, which is spheroidal graphite cast iron, then we have malleable cast iron. Now, if I see the cast iron that is forming in case of grey cast iron, if it is a ferritic grey cast iron or pearlitic grey cast iron. So, microstructure could be, you have those grains, ferrite grains, or there could be a possibility of pearlite. Okay, some pearlite presence should be there, and those graphites are actually basically in the form of flakes. So, these are graphites. These are the graphites, these are in the flake form. Here what happens, cementite breaks and then form iron, and so this is cementite Fe3C breaks and form iron plus carbon, and this carbon is nothing but graphite. Okay. Now, here also there could be a possibility of preferential dissolution of ferrite, which is nothing but ferrite, and the ferrite can dissolve, leaving behind graphite in the matrix. Okay. So, now if the ferrite dissolves, because in this particular case this acts as anode, this acts as cathode, fine. So, this anode cathode, that means anode should dissolve, cathode would stay back. Since the graphite is actually basically having a kind of flaky arrangement, and once the one layer of iron dissolves, this graphite can have interlocking between them. So, if you see from a cross section point of view, this cross section. So, if you see this part, so this part there would be individual graphites. So, these graphites will have interlocking between them. The top surface, if you see a polished grey cast iron, this is a grey cast iron. So, it will look shiny, okay, though there would be, if you compare with the steel polished surface, scratchless polished surface, and grey cast iron scratchless polished surface. In the grey cast iron polished surface, you might see a little bit of greyish nature, not very shining as you see in case of steel case, in case of carbon steel, because of the graphite presence, fine. Now, if you start with that polished surface, the shiny nature is almost lost and the surface would become very much grey color, okay. And that grey color, if you take this surface and then rub on a white paper, it just gives you the kind of appearance or the mark which you should get by having a pencil rubbing against a white paper. So, this is nothing but the graphite. Okay. Now, if you take a spheroidal cast iron, SG cast iron, so there this similar effect can happen. So, there the microstructure is, so these are let us say a ferritic matrix or little bit of pearlite is also there. There the graphites are in the form of spheroids. And interestingly, around that spheroid, if it is a pearlitic SG iron, then you will see that around that there is a white layer. The white layer, and those white layers are nothing but a pure iron or ferrite, because while graphite forms, surrounding that area it actually takes carbon and forms graphite. Okay. The cementite breaks and then that is what around that area becomes whitish. So, that is not our discussion point. But now, if we have the dealloying in this case, where the similar this graphite spheroids and ferrite, this one and this one, it will act as anode and it will act as cathode, since in the galvanic series this is having higher potential in a solution, in a normal solution or acid solution, this will be acting as a cathode. So, now there this dissolves preferentially because of the galvanic effect, and then leaving behind graphite spheroids. Okay. So, but since these are not interconnected, here if you see, it is basically, if you see under 3-dimensional picture. So, let us say this is the layer I am talking about. This is the layer I am talking about. The spheroids are actually not having any interconnection. So, because of not having any interconnection, as the layer disappears due to dealloying or the ferrite dissolution, this graphite spheroids will fall off from the surface, and it will, if you do it in a beaker, you will see that at the bottom some small black stuffs have been collected. Okay. So, this collection of black stuff you will see. So, these are nothing but graphite particles, and this happens because in this case those spheroids are not having interlocking. So, that is what it is very easy to fall off, rather than in case of graphitic case, where in case of grey cast iron, where graphites are flaky. So, that is what they have interconnection. So, they do not like to leave the surface. So, but mechanism wise both are same. So, this is one particular corrosion mode which we will call it graphitic corrosion. So, this is also falling under dealloying process, but here you see interestingly, in case of zinc copper system, we could see that copper redeposits back. In case of silver zinc system, silver redeposits back. In case of, you can go to the literature and search silver copper silver system. Okay. In case of copper gold silver system, silver dissolves, gold stays back. So, that is what you have, fantastic network of pure gold porous structure. Okay. So, there what happens, both dissolves first and then pure this noble metal deposits back. In case of copper zinc, copper deposits back. In case of silver zinc, silver deposits back. So, there we see that the preferentially both dissolves and then one pure or one noble metal noble ion deposits back, but in this case we do not have dissolution of both, rather one dissolves and the second one is left behind. So, in this graphitic iron or in the steel corrosion what we have seen there, the mechanism, the first mechanism which says that active metal dissolves and the noble stuff stays back, that particular concept is valid here. Okay. Now, coming to some of the protections what we can have in case of zinc brass system, we can use protection from dezincification. Protection from dezincification. One is we can have copper enriched brass. Their zinc could be around 15%. We can reduce dealloying to a great extent. Second, we can add little bit of tin or arsenic. Okay. Arsenic. So, what it does around 0.1% or around close to 1% arsenic, if you would add there, they actually deposits back and then prevent redeposition of copper ion. Though first layer dissolves, but after that silver arsenic redeposits back, so that it does not allow copper to redeposit back. So, one step is broken. So, whenever we have a step reaction, so what happens here, the step reactions happen, copper zinc dissolves, fine, and then copper redeposits back. So, the next step, this is stage 1. Second stage is copper plus 2 electron minus 2e, it deposits back, redeposits back. So, this is you can say stage 2. So, now if this is broken, then the first step cannot go on. Okay. So, that time, and of course, that time zinc stays there in the solution and we have dezincification, but this arsenic what it does, it forms a layer on top of copper zinc alloy and then it does not allow the second stage to happen. So, that is what it is protected. Okay. We can have for example, one such diagram, and coming to this particular effect, one can see the study that temperature and depth. Okay. So, some of the metals that, like for example, Munch metal which has around 40% zinc, then one can have which is alpha beta brass. So, then one can have naval bronze which is around 39.2% zinc and 0.08% tin. So, I said that this is around 0.1% addition. Okay. And then red brass which is around 5% zinc, 5% tin and then 5% lead. So, this one if you see, as the temperature increases, the depth of attack or the depth of dezincification is very low in case of red zinc, because here the zinc is very low 5%, and rest of the thing is copper, all the cases, fine. So, that is the advantage of having, even in case of for example, if you compare these two, only little bit of this is tin, okay. Only little bit of addition of tin has prevented the dezincification to a great extent, okay. Because you see here it was 40% zinc and here 39.2, the rest of the thing is copper and 0.08% tin, which is 0.1% tin. So, it prevents the dezincification, fine. So, that is another protection, and then another route is, in case if you have a very aggressive solution, it is better not to use brass rather than use copper nickel system. Okay. So, there cupri nickel can be utilized. This is called cupri nickel or cupro nickel. So, this is cupri nickel, which is close to 70 to 90% copper, and rest is nickel, 30 to 10% nickel. So, this is an alloy one can use in case of aggressive solution where dezincification cannot be avoided. So, these are some of the protection routes one can use. Okay. So, let me end dezincification, because I have given lot of examples from the lab, examples from the actual practical situation where the brass pipe example we have talked about. We will talk about intergranular corrosion from the next lecture onwards. Thank you.